Welcome to your next lecture, Vector Spaces and More, in Quantum Computing. This is Professor T. Freed Muhammad. This is the fourth lecture of Quantum Computing Learning at Marshall University. Let's continue our revisiting of mathematics in more depth to understand how we can use standard mathematics for classical computing, expand and have a transition for quantum computing. In this lecture, we'll be learning on topics dealing with quantum states, superposition. We will explore how these mathematical tools are used to represent quantum states and quantum operations. So let's look into quantum states. As a continuation from the previous learning, quantum states are represented as a vector or as vectors in a complex vector space. They describe the condition of quantum system, including probability of different outcomes. Imagine spinning a coin in the midair as we discussed. Its state as combination of heads and tails until it lands, or in other words, collapses. Understanding quantum states allows us to predict and manipulate the behavior of particles, which is foundational for quantum computing and is not available in classical computing arena. Superposition, let's look into this with more depth. Imagine you're playing a strategic video game where you must choose between three tactics: aggressive attack, defensive fortification, or stealth reconnaissance. In classical game theory, you analyze each strategy one at a time. Calculate the expected payoff against your opponent's possible moves and then pick the best option. If attacking gives you 5 points, defending gives you 3 points, and stealth gives you 7 points, depending on what your opponent does. You work through each scenario sequentially. Your decision is like a bet that must be set to one definite value: attack, defend, or stealth. Even if you use probability and decide to attack 40% of the time and use stealth 60% of the time based on the past data, each individual game round still requires you to commit to one specific choice before you see the outcome. Quantum superposition changes this game completely by permitting your strategy to exist in all three states simultaneously until the moment you actually execute it. Using quantum bits, your game state could be represented as a combination where you are attacking and defending and using stealth at the same time, with different probability amplitudes for each option. When a quantum game theory algorithm runs, it processes all possible strategy combinations in parallel, exploring how your superposed attack strategy interacts with your opponent's superposed defense strategy across all possibilities at once. The quantum system can evaluate countless what-if scenarios together, including complex situations where your choice of stealth might correlate with your opponent's aggressive move in ways that affect both payoffs simultaneously. Only when you measure the quantum state does it collapse into one definite strategy, but that strategy has been optimized by considering all the pathways through the game tree at once. This is why quantum computing shows promise for solving complex optimization problems and finding Nash equilibria in complicated games, because superposition allows exploration of entire strategy space before committing to final decision, potentially finding optimal plays that would take classical computers ages to discover through sequential analysis. So superposition is the ability of a quantum system to exist in multiple states at once, as I just mentioned. Entanglement links the states of multiple particles even when separated by large distances. We'll look into this concept in a little bit more depth in future lectures. That is also known as quantum entanglement. Think of a light switch that can both be on and off simultaneously, superposition, or two switches that always match each other's states, also known as entanglement. Superposition and entanglement enable quantum computers to solve problems faster than classical computers, revolutionizing fields like cryptography and optimization. So quantum operations are represented by matrices that transform quantum states. Unitary operations, which I discussed in length in the third lecture, in particular preserve the norm of these states. Flipping a switch changes the state of a light quantum operation. Similarly, changes the state of qubits in a controlled manner. Quantum operations are the building blocks of quantum algorithms, permitting us to manipulate qubits for computation and simulation. Quantum gates. Now, this is an intriguing concept. Quantum gates are unitary operations that act on qubits. They are the quantum equivalent of classical logic gates. Just as a light switch turns a light on or off, a quantum gate can flip or entangle qubits to perform calculations. Quantum gates are essential for building quantum circuits, which power quantum computers and enable advanced computation. Now let's look into the same concept that we are learning in this lecture of gaming theory, that how quantum gates can help us. Quantum gates are operations that transform quantum states by rotating them in the complex vector space we discussed earlier. And they are the fundamental instructions that quantum computers use to process information. Unlike classical computer gates that simply switch bits between 0 and 1 using basic logic operations, quantum gates manipulate the probability, amplitudes, and phases of qubits while they are in superposition. Think of a quantum gate as a precisely controlled transformation that takes your current quantum state, represented as a vector in the exponentially large space, and moves it to a new position according to the specific mathematical rules. In our gaming example, if your strategy state is a vector pointing in one direction in the quantum space, a quantum gate rotates or reflects that vector to point somewhere else, changing the probabilities of measuring attack versus defend versus stealth when you eventually collapse the superposition. Every quantum gate is represented mathematically as unitary matrix, which is a special type of matrix that preserves the total probability, keeps the norm equal to 1, and is reversible, meaning you can always undo a gate operation by applying its inverse. This reversibility is essential because quantum mechanics operates on fundamentally reversible processes, and it means that unlike classical computation where information can be erased, quantum gates always maintain all the information in the system, just transformed into different configurations. What are quantum algorithms? Now that's a great question. Quantum algorithms use quantum operations to solve problems more efficiently than classical algorithms. They leverage superposition and entanglement. Imagine finding your way out of a maze by exploring all paths at once. Quantum algorithms can explore multiple solutions simultaneously. Quantum algorithms promise breakthroughs in fields like cryptography, optimization, and drug discovery by solving complex problems faster. So let's look into one example. Let's keep learning with the game theory in a little bit more depth. A quantum algorithm is a carefully designed sequence of quantum gates that uses superposition, interference, and measurement to solve problems more efficiently than classical methods. In our gaming theory example, a quantum algorithm would work like this. First, you would use Hadamard gates to put all possible strategy combinations for both you and your opponent into superposition, creating a quantum state that represents every possible game scenario simultaneously. Next, you would apply a series of controlled gates and rotation operations that encode the game's payoff structure, essentially letting the quantum system evaluate how well each strategy performs against every counter strategy at once. The clever part is how the algorithm uses quantum interference, where the phases of different probability amplitudes either reinforce or cancel each other out. The paths leading to poor strategies like attacking when your opponent is fortified destructively interfere and reduce in probability, while paths to optimal strategies like using stealth when your opponent attacks constructively interfere and grow stronger. After running through this circuit of gates, when you finally measure the quantum states, it collapses with high probability to the strategy that represents the Nash equilibrium or best response. Famous quantum algorithms like Grover's search algorithm and Shor's factoring algorithm use similar principles, arranging gates so that wrong answers cancel out and right answers amplify, giving quantum computers potential speedups and are impossible for classical computers to match on certain types of problems. So we will be looking into those quantum algorithms in a little bit more depth in the coming lectures. The Grover's algorithm speeds up the unconstructed search problems. It finds the desired input among a list of possibilities with fewer steps than classical methods. Think of searching for a name in a phone book. Grover's algorithm can find it faster by guessing more efficiently. Why should we care? Now that's a great question. Grover's algorithm demonstrates the power of quantum computing to accelerate search tasks impacting databases and security. Now let's look into this with an example. Grover's algorithm could revolutionize how your movie streaming service, as we discussed earlier, finds the perfect match for a user's request among millions of titles in the database. Imagine a customer tells the system they want to watch that sci-fi movie from 1990s with the guy in the long black coat who can dodge bullets, but they can't remember the title. Classically, your search algorithm would need to check the movies one by one or use indexed keywords, potentially examining hundreds of thousands of entries before finding the matrix. With Grover's algorithm on a quantum computer, you would start by using Hadamard gates to create a superposition of all movies in your database simultaneously. So your quantum state represents every single title at once. Then you would apply what's called an oracle, which is a special quantum operation that recognizes the correct answer, the matrix, based on the search criteria and flips the phase of that particular movie's amplitude, essentially marking it with a quantum tag while leaving all other movies unchanged. The brilliant part comes next. You apply a diffusion operator that performs inversion about the average, which amplifies the probability amplitude of the marked correct answer while surpassing and suppressing all the wrong answers through destructive interference. You repeat this oracle and amplification process roughly the square root of n times, where n is the total number of movies in your database. If you have 1 million movies, you would only need about 1,000 iterations instead of checking 500,000 movies on average classically. After these iterations, the quantum state has been manipulated so that measuring it will collapse to the matrix with very high probability, giving you the right recommendation in a fraction of the time. This quadratic speed up might not sound dramatic, but the massive database with billions of users' content combinations of real-time personalization across millions of simultaneous users. Grover's algorithm could make searches and optimization tasks significantly faster than any classical approach. So quantum circuits are sequences of quantum gates that perform computations on qubits. They are the quantum analog of classical circuits. Just as electrical circuits control the flow of electricity, quantum circuits control the flow of quantum information. So once again, the interesting question walks in here in front of you or us. Why should we care? Quantum circuits are the foundations of quantum computers, enabling us to perform complex calculations and simulations. Quantum circuits continued. Building quantum circuits involve arranging quantum gates to manipulate qubits. The design depends on the problem being solved. Assembling a puzzle requires placing pieces in the right order similarly. That's our regular understanding. Quantum gates must be arranged correctly to solve a problem. Designing quantum circuits is key to harnessing the power of quantum computers for real-world applications. Let's look into this in a little bit more depth. Let us revisit our example of the Matrix, the movie. So, as I have already elaborated the example, so I'll not go into the details. However, we need to design a quantum circuit that acts as a blueprint showing exactly which gates to apply and when. The circuit starts with an initialization layer settling all 20 qubits to 0. So let's say if we are taking 20 qubits. Then a superposition layer using Hadamard gate to create an equal mix of all 1 million movie possibilities simultaneously. The core of the circuit is the repeated Grover iteration block executed about 1000 times, where each iteration has two parts: the oracle circuit built from CNOT and controlled rotation gates that checks if a movie matches your search criteria and marks it with a phase flip, and the diffusion operator circuit using Hadamard gates and multi-controlled gates that amplifies the marked answer while diminishing wrong answers. After all iterations, the final measurement layer collapses the qubits to the binary number representing the matrix database index, which your classical computer translates into the movie title. This quantum circuit never checks movies individually like classical loops, but instead uses interference patterns across the superposed state to find the answer through quantum parallelism, making it potentially valuable for complex optimization tasks like finding the best content recommendations across millions of users simultaneously. The applications. Quantum simulation uses quantum computers to model complex systems like molecules or materials that are difficult to simulate classically. Simulating how a new drug interacts with a virus could revolutionize medicine by predicting outcomes without physical experiments. Quantum simulation can lead to discoveries in chemistry, physics, and biology, accelerating scientific progress. Quantum cryptography. Now, this is an area which everybody is looking very keenly on. The quantum cryptography uses quantum principles to secure communication. It ensures that any eavesdropping attempt is detectable. Sending a sealed letter that changes color if opened. Quantum cryptography provides similar tamper-evident security for messages. Quantum cryptography could make communication unhackable, protecting sensitive data in finance, defense, and personal privacy. So QKD, or quantum key distribution, is also an area of interest that you can look into to further your comprehension. Quantum optimization solves complex problems like finding shortest route or maximizing resources more efficiently than classical methods. Imagine planning a fastest delivery route for hundreds of packages. Quantum optimization can find the best solution quickly. Quantum optimization can transform logistics, finance, and artificial intelligence by solving problems faster and more accurately. Let's look into this in a little bit more depth. Quantum optimization has enormous potential for improving artificial intelligence because many AI problems boil down to finding the best solution among countless possibilities, which is exactly what quantum computers excel at. In your streaming service example that we have discussed, the AI recommendation engine faces a massive optimization challenge. It needs to match millions of users with thousands of movies while considering each person's viewing history, ratings, time of day preferences, device type, and even mood indicators, all while maximizing user satisfaction and watch time. Classical AI algorithms use techniques like gradient descent, where they iteratively adjust parameters to climb towards the best solution. But they often get stuck in local optima, like finding a pretty good recommendation strategy but missing the absolute best one because there is a small valley to cross first. Quantum optimization algorithm like quantum approximate optimization algorithm, or QAOA, or quantum annealing, that's another area of research that you can conduct, can explore the entire solution landscape simultaneously through superposition. They encode the optimization problem into a quantum circuit where each possible configuration of recommendations exists in superposition. Then apply quantum gates that make bad configurations interfere destructively while good configuration interfere constructively, naturally guiding the system toward the global optimum where user satisfaction is maximized across your entire platform. The real power emerges when you combine quantum optimization with machine learning training. Training a neural network for your streaming service involves adjusting millions of weights and biases to minimize prediction error, or process that can take days or weeks on classical computers. Even with powerful GPUs, quantum computers could potentially speed up this training by using quantum circuits to optimize these parameters more efficiently. Exploring multiple weight configurations in parallel and using quantum tunneling effects to escape local minima that trap classical algorithms. For instance, if you are training a deep learning model to predict which new release will be hit based on trailer features, cast popularity, and genre trends, a quantum optimizer could simultaneously test vast numbers of network configurations to find the architecture and weights that give the most accurate predictions. So that's an area of expertise you can also go for utilizing quantum optimization. Use of tensor products combine vector spaces to create larger spaces. They are essential for describing multi-particle quantum systems. I'll not go in much detail in this area at this moment. Thinking of combining two Lego sets to build a more complex structure, tensor products work similarly for quantum states. Tensor products allow us to model interactions between multiple quantum particles, which is crucial for quantum computing and physics. Density matrix, it's a continuity of matrix learning that we have done in the third lecture. Density matrix or matrices describe the statistical state of quantum system. They account for uncertainty and mixed states in quantum machines. Imagine a weather forecast that gives probabilities for rain or sunshine. Density matrices provide similar probabilities for quantum states. Density matrices are vital for understanding real-world quantum systems, where pure states are often mixed or uncertain. Quantum measurement. This is in itself a huge research study. Quantum measurement collapses a quantum state to a definite outcome. It connects to the abstract math of quantum mechanics to real-world observations. As we discussed earlier, flipping a coin lands on heads or tails. Quantum measurement similarly collapses a quantum state to a specific result. Quantum measurement bridges theory and experiment, permitting us to test and apply quantum principles in technology. The quantum teleportation. Now that's something that I would be looking into in quite depth for my own studies. I would suggest you to conduct a research on this using Google Scholar or IEEE's Explore to expand your comprehension. However, this is just an introduction to quantum computing, so I'll not go in much detail. So the quantum teleportation transfers the state of a qubit from one location to another using entanglement. No physical particle is moved. Imagine faxing a document. The original stays, but a copy appears elsewhere. Quantum teleportation works similarly for quantum information. Quantum teleportation could revolutionize communication, enabling secure and instant data transfer over long distances. The quantum error correction. One of my PhD students is currently working on this arena. This is by itself is a huge arena of research and study. Quantum error correction protects quantum information from errors due to noise or interference. It uses redundancy and entanglement, detect and correct mistakes. Think of a spell checker that fixes typos automatically. Quantum error correction does this for quantum computation. Error correction is essential for building reliable quantum computers, which are prone to errors from environmental interference, as we discussed in our very first lecture. Let's conclude this lecture here. Vector spaces provide framework for describing quantum states, while linear operators like matrices define how these states transform together. They form the foundations of quantum mechanics. Eigenvalues and eigenvectors reveal the intrinsic properties of quantum systems, such as energy levels and stability. They help us predict and analyze the behavior of quantum states. The quantum states represent the condition of quantum systems, and quantum operations manipulate these states for computation and simulation. These concepts are the building blocks of quantum algorithm and technologies. Understanding these concepts allows us to model, predict, and innovate in quantum mechanics, shaping the future of computing, cryptography, and scientific discovery. See you in the next lecture. Happy learning.